Thank you so much for joining this lesson. We're going to discuss gas laws. This is content for physics. This is also content for chemistry. As usual, remember to subscribe. Remember to share the invitation link with your friends. You just invite somebody to this broadcast. Let's learn together. Let me post the content here. So I'm going to rush through the several laws which govern how gases behave, mostly how gases are affected when their volume is tampered with, their temperature is tampered with, their pressure is tampered with. So volume, and temperature are the main quantities which we'll be focusing on in this particular case. So kindly cooperate throughout the section. The first law is the Boyle's law. You know, the Boyle's law relates pressure. The Boyle's law relates pressure and volume at a constant temperature. How does pressure and volume vary? That is our main focus tonight, or in this particular law. There is a setup here whereby we are told to set up the apparatus as shown. So this is the figure above whereby there is a trapped air. Then this is a millimeter scale. That's a millimeter scale. Then we got oil at this point. Yeah, we are having oil there. So the oil is the one which will be used as the mark. This one will be used as the pointer. It will be showing us the level of oil, will be showing us how the colorless air has either expanded or contracted, because we can see the air column. It can be either minimized or increased depending on the changes on pressure. Something else you're supposed to know, we are having a millimeter scale here. The millimeter scale will be used to measure the air column. It is the air column which will correspond to the volume of air. Therefore, the length of the air column trapped is going to represent volume. Then pressure is going to be recorded at the pressure gauge. Connect the foot pump to the apparatus and with the tap open, pump in air until the oil raises a small but a measurable height. Then close the tap. After that, allow the air to adjust to room temperature. Then read the value of pressure on the gauge and the height h of air column, which represents the volume of the air. So the height h of the air column will correspond to the volume of the air, because the bigger the air column, then the greater the volume it is representing. The air column is short, then it is a shorter volume or a smaller volume. Then there is the glass tube is having a uniform section. Yeah, so let's look at the next step. Now you repeat that after your initial pressure, you record initial pressure and the corresponding value of height, which is representing volume in this particular case. Then now you can work out now the reciprocals of h, the reciprocal of h per centimeter. Then now after that, you can adjust the values of pressure. After you adjust the values of pressure, you adjust the values of pressure on the pressure gauge so that immediately you adjust the pressure to a new value, you confirm the new column of air, and you realize that pressure variation leads to an automatic variation in the column of air, which is volume in this particular case. Therefore, varying the pressure automatically varies the volume of a given mass of a gas. And now, generally, just to state the Boyle's law, it states that the pressure of a fixed mass of a gas is inversely proportional to its volume at a constant temperature. Listen to that mathematical statement. The pressure of a fixed mass of a gas is inversely proportional to its volume at a constant temperature. Therefore, temperature is constant in Boyle's law. Remember, mathematically, now we can put down this statement and say pressure inversely proportional. So we pick the reciprocal, inversely proportional. Yeah. Remember, we can substitute the symbol of proportionality with a constant and an equal sign. So this implies that pressure is equivalent to a constant K when multiplied by V, or multiplied by the reciprocal of V, it just becomes constant out of V. And now from this, we can also say that we make the constant a subject by multiplying through by V. Therefore, pressure times volume equals to a constant K, where K is a constant. In this particular case, where K is a constant, then it's good for you to understand that if you, let's assume we had taken a case here whereby there was a pressure 1, then it gave us a corresponding volume 1. If you adjust the pressure to a new value, pressure 2, and it also gives you a corresponding new value of volume, such that you are having a pressure 2 and a volume 2, the two are going to give you the same constant. Therefore, there is a constant relating how pressure is varying with volume in this particular experiment. And therefore, since with a certain pressure and the corresponding volume, we get a constant, and after varying the pressure to get a new volume, we are also having the same constant, then we will be very right to equate pressure 1, volume 1, equivalent to pressure 2, volume 2. So that is a very sensitive equation which a student is supposed to value. A very sensitive equation. We continue learning. Yeah, it's good I remind my followers of our program here for purchasing airtime. If you need airtime of any amount for any network, you just go to your M-Pesa, Lipa na M-Pesa, then the pay bill number is 737356. Account number is the phone number that you would like to purchase airtime for. Then after that, now you enter the amount you'd like to spend as airtime. Then you complete the transaction. The airtime is going to reflect instantly. So please utilize this facility and invite your friends to utilize the same. We continue with the Boyle's law of an ideal gas. Yeah, we are saying pressure 1, pressure 2, and volume 1, volume 2 are the initial and final values of pressure and volume respectively. Now we can also represent this comparison graphically, whereby we are saying if the experiment on Boyle's law is repeated at different fixed temperatures and the results plotted, isothermal curves are obtained. Isothermal curves are obtained. Look at this. Pressure and volume are inversely proportional. Now that they are inversely proportional, we expect curves. So in this particular curve, it is good for you to know that when the experiment is performed at whatever constant temperature, we get a smooth curve. And assuming that we began with temperature T2, this is the curve that we would have obtained, the green curve. The green curve is the initial trial whereby we have gotten a curve. Now, if we try the same experiment at a constant temperature, but which is less or smaller, temperature which is smaller than temperature 2, then the curve is going to be above the first one. But if we try such that the new temperature under which we are performing the experiment is now greater, that's T1 now, is greater than the initial value, then the curve is going to be here. So that's how we get the curve. Sometimes you'll be told the graph below shows the variation of pressure and volume for a given fixed mass of a gas at a constant temperature. Let me give this let me just display this possible question for the students who are preparing for their KCSE physics paper 1. Yeah, physics paper 1. So you are told simply that this is pressure, this is volume, and a practical was done for such a variation, and this graph was obtained. Just a smooth curve like that. Now you are told on the same axis, draw a curve to show what would have been observed if the same experiment was performed at a temperature slightly higher. Slightly higher. Therefore, slightly higher, we expect it to be here. That's where we expect. If you are told that it was repeated at a temperature which is below the one plotted, then we expect it to be here. Yeah, we expect it to be at that point. So that is it. Now, if we take the reciprocal of V, then we are going to get straight lines now. We are going to get straight lines. Yeah. And again, you can see if you repeat when temperature 3 is less than temperature 2 and temperature 2 is less than T1, this to mean that T1 is the greatest, T3 is the least, then we have now the average T2. This is to tell you that if the straight line for T2 is drawn and you are told that this experiment was later repeated at a temperature slightly higher, then we expect the curve to be T1. If it was repeated at a temperature just below T2, we expect the curve to be on this side. So those are possible questions. Please remember to master them. Look at now this example, which is a calculation. Look at this example now in a calculation form. I want us to compute it together. Make sure you are following. The diagram below shows an air bubble of volume 2.0 cubic centimeters at the bottom of a lake 40 meters deep. What will be its volume just below the surface? Just below the surface. If, this is one is a if the atmospheric pressure is equivalent, if the atmospheric pressure is equivalent to a height of 10 meters of water, equivalent to a height of 10 meters of water. Now, when you are told 10 meters of water, and that is the value of atmospheric pressure, you know we are supposed to know that the lake is open. Therefore, apart from water pressure acting on the air bubble, there is also pressure due to the atmosphere. So the total pressure working on the bubble while at the bottom is pressure due to the air column, to the water column, sorry. This is water. So pressure due to the water column plus the atmospheric pressure. But exactly at the surface of water, when it is almost emerging, when the bubble comes up here, now the pressure acting on it is squarely, the pressure due to, the pressure due to the atmosphere. So now we can say that 10 meters height equals to 1 atmosphere. Atmospheres are units for measuring pressure, just together with millimeters of mercury, centimeters of mercury, pascals, Newton per meter squared. Yeah, those are all units for recording pressure. Therefore, at the base here, whereby there are 40 meters, then it means we will be having 4 atmospheres. But now the pressure one, which is originally acting on the bubble, is going to be, we add 1 atmosphere, that is a pressure due to the atmosphere, plus the 4 atmospheres due to water. That is a total of 5 atmospheres. But the new pressure at the surface will be squarely the 1 atmosphere due to atmospheric pressure. 1 atmosphere. Now, volume 1 is given here, 2.0 cubic centimeters when it was at the base. What about volume 2 when the pressure had changed? You remember this equation? That pressure 1 V1, this one should be 1, sorry. Pressure 1 V1 equals to pressure 2 V2. Therefore, with that, we can say now pressure 1, which is 5 times the volume of 2 equals to multiplied by the unknown V. And through that, you will discover that the new volume now becomes 10. Even this question, according to the relationship between pressure and the volume of an ideal gas, we are expecting at the surface where pressure acting on the bubble will have reduced, the volume will, on the other side, have increased. So as the pressure decreases towards the surface, the volume of the air bubble is expected to increase. Let's look at one more example. Yeah, one more example. The volume V of a gas at pressure P is reduced to without change of temperature. That means volume is changing at a constant temperature. That means the gas is obeying Boyle's law. Determine the new pressure of the gas. Determine the new pressure of the gas. Remember, now equals to P. Volume 1 equals to V. And we have the volume 2 given as 3 by 8 of the original V. In other words, in this equation, if we are to substitute, we will just have PV equals to unknown P2 times the new volume 3 over 8 V. So how do we remain with this pressure 2? This will be, pressure 2 is going to be PV. And now to remain with P2, we are supposed to multiply with it. This one is a mathematical step. Please be careful. multiply by 8 out of 3V. So we multiply this by 8 over 3V. So the value of V will cancel out, and we'll be having 8 over 3, the value of original pressure. So the new pressure in simpler terms is going to be, we can change 8 over 3 now. You cannot leave it as a fraction like that. 2.667 original value of P. So that is how the new pressure will be obtained. We can also check at another frequently tested question, which actually I'm planning to emphasize on it very much. A column of air 26 centimeters long is trapped. 26 centimeters long is trapped by mercury thread 5 centimeters long as shown. So in the first diagram A, we are having 5 centimeters of mercury and 26 centimeters of air trapped. You can see now the tube is upright. When the tube is inverted, as you can see in figure B, the air column becomes 30 centimeters long. What is the value of the atmospheric pressure? What is the value of the atmospheric pressure? Now, let us analyze this very carefully. I will also give another scenario whereby the tube is laying horizontally. So look at the first case. The air column represents the volume of the air. Therefore, we can say volume 1 is equivalent to 26 centimeters. Then pressure 1 is going to be, the total pressure acting on the air column is going to be pressure due to the mercury plus pressure due to the atmosphere. Now, pressure due to atmosphere is unknown. Pressure due to atmosphere is unknown. We can let it be X. So in this particular case now, you say pressure 1 equals to pressure of the mercury is 26 centimeters of mercury. We said centimeters of mercury is an approved unit for recording pressure. Centimeters of mercury plus unknown pressure. Now we can use uniform units of centimeters of mercury, whereby we can say even the atmospheric pressure can be expressed. The unknown atmospheric pressure can also be expressed in terms of centimeters of mercury. Let's now look at the second case in part B. In part B, we can say that the new volume, volume 2, is now becoming 30 centimeters. It is now 30 centimeters to represent the volume. That's a clear indication that pressure must have reduced. Pressure must have reduced. Therefore, what will be the pressure 2 now? Pressure 2 in this particular case is going to be given by, pressure 2 is going to be given by, you see, the tube is still open, therefore atmospheric pressure is able to access. But now this time round, the weight of the mercury is acting downwards. If the weight of the mercury is acting downwards, then the resultant pressure, which is pressing the air column, is the difference between the pressure due to the atmosphere minus pressure of the weight of mercury. So it is now the difference in pressure. This is one evidence that the atmospheric pressure is greater than the 5. Actually, there is a mistake here. Sorry. I am supposed to recognize this one as 5 centimeters of mercury. Therefore, the atmospheric pressure is greater than the 5 centimeters of mercury. Therefore, I'll be talking about unknown atmospheric pressure, and we subtract the 5 millimeters of mercury so that we may know the 5 centimeters of mercury, so that we may know the resultant pressure. Atmospheric pressure is acting upwards, but pressure due to the mercury column is acting downwards. Therefore, the net pressure now, the resultant pressure is going to be the difference. So now with this, we remember that according to Boyle's law, P1 V1 is equivalent to P2 V2, meaning if we take 26 multiplied by 5 plus x, this will be equivalent to, we take 30 on the other side, yeah, then x minus 5, x minus 5. So 26 by 5 is going to give me 130 plus 26x equals to 30x minus 150. Grouping like terms together, we will have 130 plus 150, that is 280, yeah, equivalent to 30 minus 26, we're going to get a 4x. So to remain with 4, I will take 280 and I divide by 4 to remain with x. Sorry, to remain with x, I'm supposed to divide through, and I'm getting 70 centimeters of mercury. This is now the value of atmospheric pressure at that particular point. Centimeters of mercury. Those are units of pressure now. Centimeters of mercury. So that is how the question is supposed to be done. I must give students a precaution. Let it be known that when the tube is upright, pressure is usually given by, look at this, pressure is given by addition of the mercury column plus atmospheric pressure. When it is upside down, as you can see, when it is upside down, pressure is given by atmospheric pressure minus pressure of the mercury thread. Remember, you can be asked a simple question, give us a reason why the mercury thread, though the tube is inverted, the mercury thread did not pour out. This is because the pressure exerted by atmosphere overcomes the pressure due to the mercury thread. Now, when the tube is horizontally lying like this, and we have our column here of mercury, then we have our air at this point. In this case, we usually say that atmospheric pressure is entering the tube, but the weight of this particular mercury thread is acting downwards. The mercury is acting downwards. Therefore, the significant pressure which is compressing the air column, in this case, pressure is simply equal to pressure of the atmosphere. So pressure of the atmosphere when the tube is horizontal is the only pressure acting on the air column, because weight of the mercury, in this particular case, because weight must act downwards, then now the weight of the mercury thread acting downwards will have no significant difference or will have no significant impact on the air column. So that is something you're supposed to know as you interact with this particular question. Yeah, thank you so much for being around. I can read your messages. We can continue learning. Remember to share so that we may invite a few friends. Yeah, so those are examples on Boyle's law. We can now check another law called Charles' law of an ideal gas. As we continue learning about Charles' law, let people be reminded of our program here. Access airtime of any amount at any convenient time. You go to the M-Pesa for any line. The pay bill number is 737356. Then the account number is your own line. Your own line is the account number, be it Safaricom, Telcom, Airtel, you just enter the number as the account. Then after that now you can enter the amount, you complete the transaction, and you receive your airtime instantly. Remember, for consultations, you can just reach out through 0704 sorry, I'm trying to adjust here my screen. Yeah, 0704 153366. This is the line you should reach out through in case you have any queries. Yeah. Now, Charles' law compares temperature and volume of an ideal gas at a constant pressure. So in this case now, it is pressure being held constant, so that temperature and volume may be compared. A variation in temperature may affect the volume of a gas. Yeah, such a case. Now look at this. This is an elastic band. I'm just examining the experiment here, just the setup, because definitely we are going to assemble apparatus as shown on this diagram. There is a capillary tube. The capillary tube is, of course, to ensure that the air inside, in case there are changes in the volume, it will be sensed very easily because the tube is thin. Capillary tube means a thin tube, a narrow tube for that case. So if the tube is narrow, any changes on the column will be sensed very quickly. Then now, inside the tube, there is something we're supposed to know, that there is concentrated sulfuric acid. Now, concentrated sulfuric acid is going to have two roles in this particular experiment. One, it will be acting as a pointer. It is the one we will be observing the sulfuric acid index. It is the one we will be observing so that we may know the height of the air column, and it is also the one which is going to serve as a drying agent so that the air in the experiment is dry. Then there is a ruler, of course, calibrated in millimeters and centimeters. That one will be used to measure the air column. There is a thermometer. The thermometer here is to check the temperature changes. Remember, this one is on hot water or even water which can be having a heater. So that either we can begin when the temperatures are very hot and we check what is happening to the temperature. Okay, whatever is happening to the volume of the air as the temperature goes down. Or we begin when the temperatures are low, then we heat and we observe what happens to the columns of the air as the water temperature rises. Now introduce concentrated sulfuric acid deep into a glass tube to trap air in the tube. To trap air. The tube is sealed on the lower side, and now in the upper side, we are introducing concentrated sulfuric acid. Remember, the concentrated sulfuric acid will have two responsibilities. One, to absorb any moisture, that is a drying agent. And two, that sulfuric acid index will be serving as the pointer. It will be showing us the columns of air in the narrow tube. Now attach the tube, the thermometer, and the ruler using a rubber band. So the thermometer, they are together so that we may monitor the progress. We also progress of the air in terms of temperature, and also using the ruler, we can observe. Using the ruler, we can observe the length of the air column. Assemble the apparatus as shown. Now the setup is there. We have already discussed it. Assemble the apparatus as shown. Yeah, then after that, now you record the room temperature and the corresponding height of air. Assemble the apparatus. then record room temperature and the corresponding height. So those are the initial values. You start with room temperature and the corresponding height. So that after heating, you consider change in temperature after a given time. You record new temperature, then the new column of air. You continue heating after a certain interval again. You record the new temperature after heating and the corresponding height of the air column. Like that until you collect some sufficient data which can be represented graphically, from which some analysis can be drawn, such that we can make comparisons. Yeah, such that we can make comparisons. Thank you for being around. I can see you people. Thank you. Thank you. This is really great. Remember to subscribe. Remember to share. Thank you so much, Kennedy Diampo. A long time, sure. It has been a while. Thank you for getting back to our live broadcast. Roman 1. We are given some notes here. The sulfuric acid index serves as a pointer on the scale, as well as a drying agent for the air. Drying agent, and it's also a pointer, that is the sulfuric acid. Look at this. The pressure of the trapped air, the pressure of the is the same as the atmospheric pressure plus pressure due to the sulfuric acid, which remains constant throughout the experiment. Therefore, we are performing the experiment under a constant pressure. What is varying here is temperature and volume. What ensures that the pressure is constant? The tube is open, therefore, pressure exerted by the column of concentrated acid together with atmospheric pressure is constant throughout all the stages. Whenever results are being taken, pressure is just constant. Before taking the readings, start the water bath so that the temperature of the gas is equal to that of the bath. Then plot height against temperature. Yeah, plot height against temperature. It's good to know that temperature can be in the Celsius scale and temperature can also be in the Kelvin scale, the absolute temperature, that is. Absolute zero refers to the lowest temperature of a gas at which the volume of a gas is assumed to be zero. That temperature is negative 273 degrees Celsius, which is the equivalence of the 0 Kelvin. The Kelvin scale of temperature starts at negative 273 degrees Celsius. That is the 0 Kelvin, and it is called the absolute scale. Now, it is good for you to know that whenever you are using the relationship between temperature and volume for Charles' law, whenever you are relating, there is calculations you'll be doing, and it's good to know that we'll be using absolute temperature, or simply temperatures must be expressed in the Kelvin, more so when you are doing calculations. In any other argument, you can use any scale. Look at this now. Look at this. Volume against temperature in Kelvin. This is the graph that we will get. This is the graph that we are going to get, showing that volume and temperature are directly proportional. Directly proportional. But in case you use the Kelvin scale, look at it this way. I think they have drawn it somewhere. In case you use the Kelvin scale as displayed in this part, in case we will also have this is volume in cubic centimeters. Then now the graph is here, temperature in degrees Celsius. Remember, the equivalence of degrees Celsius to 0 Kelvin is negative 273. Therefore, the graph axis at some point, but if you prolong, or rather if you extrapolate the line, then it's going to cut the temperature axis at a value equivalent to or approximately negative 273, which is the same as the 0 Kelvin. Therefore, be careful in case the blank axis is drawn and you are told to sketch a variation between volume and temperature, and the temperature is in degrees Celsius, then you should be able to know that the line is going to cut the temperature axis at negative 273, while on the other axis, whereby it is a temperature in Kelvin, it will be exactly at zero. Exactly at zero. The reason why it is dotted here is because it is not practical to have the temperature dropping to zero when the substance is still gaseous. We expect by the time the temperature is becoming 0 degrees, the substance will have maybe it will have condensed into a liquid or something, but a gas realistically cannot take such a temperature. So that is what you're supposed to know. The Charles law mathematically now, from the graphs, we can see that there is a direct proportion. So that's why we can say that the volume of a fixed mass of a gas is directly proportional to the absolute temperature. Absolute temperature, or simply temperature in the Kelvin scale at a constant pressure. At a constant pressure. So mathematically, we are saying volume is directly proportional to temperature, whereby we can say volume equals to a constant times T. And to express our constant K, then volume out of T, volume over T. So the constant K can be given by volume over T. And in case you vary temperature, for you to get a new volume, you discover that the ratio of that new volume and the new temperature will give us the same constant. And that is why we are saying for this particular case, volume 1 out of T1 is the same as volume 2 over temperature 2. Something that you must understand. Something that you must understand. So this is the relationship now which we will be using, and we must take note that temperature must always be in the Kelvin scale. In the Kelvin scale. Therefore, we can check a few calculations now using this relation. Let's now get to let's get to the examples. Example 4. 0.02 cubic meters of a gas at 27 degrees Celsius is heated at a constant pressure until the volume is 0.03 meters cubed. Calculate the final temperature of the gas in degrees Celsius. Now, what we're supposed to take precaution here is that this is a trap. Temperature in degrees Celsius. Any computation must be done when temperature is in the Kelvin scale. That is something you should note. Therefore, we will perform the question using the Kelvin scale, but finally, we will be converting to degrees Celsius. Look at this. 27, we need to add 273 so that we get 300 Kelvin. Because to convert temperature to Kelvin scale from the degrees Celsius scale, we just add 273. That, for this case, now we are getting 300. In case we are converting from the Kelvin scale to the degrees, to the centigrades, that is degrees Celsius, we need to subtract 273. Therefore, we have now this one as our temperature 1. Then what is the volume 1? Volume 1 is 0.02 cubic meter. What about volume 2? 0.03 meters cubed. Then now we can get to the relationship from from the Charles law of an ideal gas. V1 T1 equals to V2 out of T2. Therefore, we need to say V1 0.02 out of temperature 1300 equals to V2 0.03 divided by T2, which is unknown. We can do a cross multiplication. We can use very many mathematical steps now for us to arrive at our T2. Yeah, for us to get our T2. So we can do a cross multiplication such that we are talking of, let me show you what I mean. We are talking of 0.02 T2 equals to 300 multiplied by 0.03. Then for you to remain with T2, we have to divide through by 0.02. Therefore, we need to take 300 multiplied by 0.03, then we divide by 0.02. This is going to be 450 Kelvin. That is how we are supposed to compute the calculation using the Kelvin scale. Then after that, now, if there are further instructions, like now leaving the final temperature of the gas in the degrees Celsius, now the temperature 2 can also be equivalent to 450. We subtract 273. What will this give us? 177 degrees Celsius. So that is the temperature in the demanded units. Get airtime any amount for any network in Kenya, Safaricom, Airtel, Telcom, by going to the M-Pesa, Lipa na M-Pesa. Then the pay bill number is 737356. Account number being the phone number that you are purchasing airtime for. Then you enter the amount, you complete the transaction, the airtime shall reflect instantly. Thank you so much. You can utilize the facility and involve your friends in the same. Look at example 5. A mass of a gas of volume 750, that is a cubic centimeter, is heated at constant pressure from 10 degrees Celsius to 100 degrees Celsius. What is the final volume of the air? So what are we having in this case? Initial temperature, final temperature, and initial volume. We just want final volume, or rather volume 2. So we say volume 1 is equivalent to 750. Now temperature 1 equals to 10 degrees, whereby we have to add 273. And this is going to give us 283. Then we talk of temperature 2, heated to 100. Therefore, we talk of 100 plus 273, just to make it 373. This Kelvin, this is cubic centimeter. Therefore, with such an analysis now, we can get to the formula whereby we are saying V1 T1 equals to V2 out of T2. Therefore, now I'll be able to take 750 out of 283, equivalent to V2 unknown, equivalent to remain with V2, cross multiplication. V2 after cross multiplication is going to be 988.5 cubic centimeters. Temperature having increased, we expect an increase also in the volume of the gas, Then we have now the pressure law. Yeah, we are winding up. Let's look at the pressure law of an ideal gas. Look at this wonderful experiment here. Set up the apparatus as shown. We are having the pressure gauge, and it's good for students to know that an alternative apparatus to the pressure gauge can be the Bourdon gauge. So in case you see Bourdon gauge as an apparatus in these experiments on gas laws, just know that they serve the same purpose of measuring pressure of an ideal gas. Now we have a thermometer here. Definitely this one is to record the progress in the temperature, and we have a source of it. This is water. The water must be stirred using the thermometer to ensure that heat is uniformly distributed. Now there is a air inside here. We got some air, a mass of air there, dry air of course. So now when the air is heated, we'll be able to note whether there is a change in temperature and also a variation in the pressure as recorded by the Bourdon gauge. So we use the thermometer to know the variation in temperature, and we check corresponding variation in pressure using the pressure gauge. Therefore, the pressure law compares absolute temperature and the pressure of a gas. Record the initial temperature and pressure of the pressure readings. Yeah. Then after that, what are we supposed to do? We heat the water bath gently and obtain at least 7 more pairs of readings at suitable temperature intervals. You record temperature, the pressure, temperature, the pressure, temperature, corresponding pressure, until you fill the table with the sufficient items or sufficient values. Then now you record your results here. It's good to know that the air in the tube connecting the gauge at lower pressure than the air in the flask. This should be as short as possible. Should be as short as possible. So the tube should not be very long, because the tube might contain some air which is at a different temperature from the one inside here. So to avoid that as a source of error, then we ensure that the tube that we are using is as short as possible, so that if it contains air at a different temperature, that air will have negligible effect to the general temperature inside the flask. Now you are supposed to plot after the table. Now you plot pressure against temperature, and when the temperature is in the Kelvin scale, we will have a line through the origin. When the temperature is in the degrees Celsius, we expect the line to cut the vertical axis at a point towards the equivalence of 0 Kelvin. The equivalence of 0 Kelvin is negative 273. So that is what we expect. Pressure law. Pressure law states that, we have already seen graphically when the results are represented there is a straight line, meaning direct variation. So the pressure of a fixed mass of a gas is directly proportional to the absolute temperature, simply temperature in the Kelvin scale, at a constant volume. At a constant volume. Therefore, pressure is directly proportional to temperature in Kelvin. So pressure we can have a constant times T, a constant over T. And it's good for you to know that in case now you take a new value of temperature, which will lead to a new value of pressure, and we take the ratio, we will get the same constant. So the constant is sustained, and that is why we have the constant relating pressure. That's why we have a straight line. The gradient is uniform all through. So the constant relating pressure and temperature is a constant. It is a constant. And whenever you vary pressure and the corresponding temperature, we expect the constant to be preserved. Therefore, because of that, the ratio of P1 over T1 will still be the same as when we take a new sample with pressure 2, when we divide it with the corresponding temperature 2. So that one is supposed to be noted. And now with that, we can take down a few examples. A cylinder contains oxygen at 0 degrees Celsius and 1 atmospheric pressure. So that is temperature and pressure. What will be the pressure in the cylinder if the temperature rises to 100 degrees Celsius? So the temperature is changing from 0 Kelvin, which is 273. 0 degrees Celsius is 273 Kelvin. That is temperature 1. Temperature 2 is going to be 100 plus 273, 373 Kelvin. 373 Kelvin. 373 Kelvin. Then now with that, we can see that the original pressure was 1 atmosphere. So pressure 1 equals to 1 atmosphere. What about pressure 2? Unknown. And we have said when we take, according to this expression, P1 out of T1, P1 over T1 equals to P2 out of T2. What is not known? P2, because P1 is 1 atmosphere out of temperature 1273. This one is equivalent to P2 unknown out of V2, out of, temperature 2373. To remain with P2, we have to multiply through by 373. So 373 out of 273. This is 1.366. 1.366 atmospheres. Pressure in atmospheres. To be pressure in atmospheres. There is another question here, still on the same, the pressure law. At 20 degrees Celsius, the pressure of a gas is 50 millimeters of mercury. At what temperature would the pressure of the gas fall to 10 centimeters of mercury? Therefore, we are talking of a temperature 1 being 20 degrees Celsius. So we make it Kelvin by adding 273, which will make it 293 Kelvin. Then now, those are two different pressures. What are we now? So temperature 2 will be what? When we take pressure 1 and we divide by temperature 1, we get pressure 2 divided by the. Therefore, to get temperature 2, we can cross multiply 50 T2 equals to 10 by 293. And how do we remain with temperature 2? We divide through 10 by 293. We divide by 50. I'm getting 58.6. 58.6 Kelvin. That is the new temperature. Yeah, that is the new temperature. Unless we have been asked, there is no urgency in converting to degrees Celsius. The temperature is already settled in the SI units. Yeah, thank you. Thank you for being around. Thank you for being around. We can continue winding up with our lesson, but I hope tonight you getting something. I need a lesson on trigonometry 3. Check on our channel. Those topics have already been uploaded. Shifting Grades Online School for yourself. Now, there is equation of state, whereby we can also call it the combined equation for the gas laws. Remember, you can access airtime for any network that is working in Kenya. Safaricom, Airtel, Telcom, by going to the M-Pesa, Lipa na M-Pesa option, then you go to the pay bill number 737356. Anybody can master this, 737356. Then the account number is your own phone number. The account number is your own phone number. Then you enter the amount now that you want to spend as airtime. You proceed with the transaction and you receive your your airtime instantly. You receive your airtime instantly. So let's now look at the combined, which now gotten from the three gas laws, whereby we have now to relate pressure, volume, and temperature. And we say that pressure times volume divided by the temperature is usually a constant. That means now pressure 1 V1 out of temperature 2 is the same as pressure 2 V2 out of temperature 2. When you vary now all the three quantities, that is how they relate. So from that we can get a few questions. Let's do the first one. So the first one, we are told that a mass of 1200 cubic centimeters of oxygen at 27 degrees Celsius and pressure 1.2 atmospheres is compressed until its volume is 600. And its pressure is 3 atmosphere. What is the Celsius temperature? This one is a very key statement. What is the Celsius temperature of the gas after the compression? Remember, we have said P1, V2 out of T is a 1.2 atmosphere. Let me compute this 1.2. Let me put it keenly. 1.2 multiplied by the first volume, 1200. So the first temperature is 27 degrees Celsius. We need to add 273. This is 300. So temperature 1 is 300. This is equal to pressure 2, which is 3 atmosphere, multiplied by volume 2, which is now compressed to 600. 600 out of the unknown temperature 2. So let's get temperature 2. For us to get temperature 2, we have to cross multiply 1.2 by 1200. 1.2, sorry, 1.2 by 600 by 300. Yeah, after the cross multiplication, how do we remain with T2? Who tend to get stuck? Those are the people I'm helping to know how to maneuver through unknowns. Sorry. I'm checking something on my screen. Just give me a minute. Yeah. I think things are back. Yeah. So I'm talking of T2 being equivalent to 3 by 600 by 300. Then we divide this by 1.2 and 1200. So from this, we are going to get 375 Kelvin. And now, what is the examiner talking about? The Celsius temperature. So now we have to compute back temperature 2 into the degrees Celsius by taking 375 minus 273, and that will be 102. 102 degrees Celsius. So that is the new temperature. We are supposed to be very careful on that. You're supposed to know that in the computations, temperature is supposed to be strictly in Kelvin. But now the questioning, which is a Celsius temperature, that might tempt a student to work with the Celsius, the degree Celsius, which will be a very big mistake. Finally, as we wind up, there is a thermolecular explanation of all the gas laws, or rather the kinetic theory behind the three gas laws. This is what we'll be going through as we finalize Boyle's law and the kinetic theory. If the volume of a vessel containing a fixed mass of a gas is halved, the number of collisions per unit volume will be doubled, because the longer they were taking to go and hit the walls of the container has now been brought closer. Therefore, you find within a fixed time, the collisions which could have been made are now being made times two. The number of collisions per unit time, the number of units per unit time, and therefore the rate of change of momentum. So we can see when we reduce the volume, is increasing because you have increased the per unit time. The collisions the gas particles are making with the container per unit time, which are the ones which results to pressure, have been increased with a decrease in the volume of the container. And that one verifies, that one verifies the Boyle's law. You can also check what happens to the Charles law. What happens to the Charles law? When a gas is heated, the velocity of the molecules also increases. It's the temperature. If the volume of the container is constant, then the pressure on the walls would increase, because is being constant, but the temperature has increased. So you find collisions are increasing per unit time. But what are we saying in this case now? But since Charles' law requires the pressure be constant, then the volume must increase accordingly. The volume must increase accordingly, so that although the molecules are moving very fast, the number of collisions at the walls of the container per unit time is reduced, since the distance between the walls is increased by increasing the volume. So we increase the volume to ensure that the pressure remains constant. Yeah. The pressure law, which is the final one. In gases, pressure is as a result of bombardment of the walls of the container by the gas molecules. When the molecules of the container, or when the molecules of the gas bombard, bombarding is a colliding with and rebound from the walls of the container, a change of momentum takes place. The number of bombardments per unit time constitutes a rate of change of momentum, which according to Newton's second law of motion will constitute a force. This force per unit area emerges as the pressure of the gas. When a gas is heated, if the volume is constant, the molecules will bombard the walls many times or many more times per unit time and with greater momentum. The total rate of change of momentum will therefore increase. The resulting force per unit area, which is the pressure, will also increase. Gas laws have some limitations. When explaining the gas laws using the kinetic theory, both the size of molecules and the intermolecular forces are assumed to be negligible. We assume that the molecules of gases are not held together by any forces for the gas laws to hold. Real gases have molecules with definite volumes, and therefore the idea of zero volume or zero pressure is not realistic. Real gases get liquefied before zero volume is reached. That's why I was saying before we get a volume equivalent to zero, the gas will have already condensed. This departure from the gas law is so particularly true at low temperatures and high pressures. A gas that would obey the gas laws completely is called a perfect gas or an ideal gas, something which is just imaginary. We can look at characteristics of real gases and ideal gases. An ideal gas is a perfect gas, which for this case I would say it's just an imaginary gas. Ideal gases obey all gas laws under all conditions of temperature and pressure. A real gas obeys only at low pressures and high temperatures. For ideal gases, the volume occupied by the molecules is negligible as compared to the total volume of the gas occupied. That is a gas which is able to occupy the laws, to obey the laws. But on the other side, we say the volume occupied by molecules is not negligible as compared to the total volume of the gas. Finally, we are also saying that the force of attraction among the molecules are negligible. We assume that molecules of a gas are not attracted to one another. But on the other side, we are saying the forces of attraction are not negligible. They are there at all temperatures and all the pressures. So that is all tonight. Thank you so much for following us. Remember to subscribe to this platform for more. Remember to always tune in whenever we have a live stream. For more updates, be a subscribed member. Purchase airtime of any amount. Just go to your M-Pesa, Lipa na M-Pesa, then the pay bill number 737356. Account number is your own phone number. Then you enter the amount you'd like to spend. Then you complete the transaction and receive your airtime instantly. Thank you so much for the continued support. Have a good night.